Okay, so this clip is about the analog of one-step transition probabilities, but in a continuous setting. So there's a question mark as to whether such a thing can exist, and let's discuss it. In discrete time Markov chains, there was a very natural way in which time evolved. It sort of evolved in steps or turns. Think of me flipping a coin. Every single coin flip increments time by one, and so there's a very natural unit of time or a natural progression of time. And provided that the chain was homogeneous, in accordance with this kind of step or turn nature of discrete time, we had one-step transition probabilities, which were numbers, right? Any numbers that are non-negative and satisfy this distribution property for each state, formed one-step transition probabilities, and you had kind of all of a sudden there is a Markov chain, just given these, numbers. Satisfying these properties here. In continuous time, there's no like natural time increment. Time is continuous. You can't like say one step or one turn, or time moves continuously. And these were our definitions for for the CMTC, or at least a homogeneous one. One was as a Markov process with step function paths. That's the picture below me, with these transition probabilities that you notice are defined, once again in terms of all states at all times. So this is by no means does this look anything like a one-step transition probability, because you need to keep infinitely many of these things, right? It's a whole function here, so it's a much more complicated object comparing to the one-step transition probability. There is something a little bit more similar in the second definition. So second definition is, again, you have a rate for every single state. That rate governs the rate of an exponential waiting time that you wait for in each state. And then there's the embedded chain, which actually does have one-step transition probabilities. So we kind of taken away some of this complexity of keeping infinitely many things, and we're now keeping one-step transition probabilities plus a bunch of numbers, rates for each state. So it's a little bit better, but still not as clean as kind of things were in the discrete time setting. So I'm asking there, is there something as simple as just one-step transition probabilities that summarizes all this information? And perhaps surprisingly, the answer is yes. This is called the infinitesimal generator. So it's difficult to say. You could sometimes just say generator if you don't like the word infinitesimal. I'm going to try to explain where this word comes from. But for now, just to give you the definition, sort of, the first thing you need to think of as soon as you hear the word generator for a continuous time Markov chain, and also, and by the way, this is for a continuous, for homogeneous Markov chain. What it is, it's just the derivative of the transition probability. So we have these transition probabilities for all states and all times. We're going to take the derivative and evaluate the derivative at 0. That's one definition. Here is another definition in terms of the embedded chain, and it's a one-step transition probability and these rates that every single state has. This is a little bit simpler. So here, Rxy, the generator for the states xy, is defined to be minus Rx, so negative of the rate of the particular state whenever x and y are the same. And then is defined to be this product here when the states are not the same. So, these are just definitions. We're going to try to unpack these in future clips, but for now, it's just something to keep in mind. So on the level of definition only, as I say there, these two are actually mathematically equivalent. I'll show you why that's the case. One quick note before I move on to the next clip is that in the time inhomogeneous setting, which we're not going to discuss much, this would actually be a function of time as well. But for now, we're thinking of homogeneous continuous time Markov chains, where, again, back in the discrete time setting, there were one-step transition probabilities. Right? If the thing was not homogeneous, then we'd lose this as well. So we're going to stick with homogeneous time continuous time Markov chains, and we're going to look into why these definitions are what they are, what the word infinitesimal means, what the word generator means, and so on and so forth. So that's the next clip.